Thanks very much. I realized yesterday, of course, that I wanted to say much more than I'd actually said. So let me just maybe use now the opportunity to recall a couple of things that I said yesterday and add some more detail. So recall that what the setting was. So we had a globally hyperbolic spacetime, mg, globally hyperbolic. And there was some vector bundle on it that I called E. And we had a normally hyperbolic operator acting on sections of this bundle. This is normally hyperbolic. And that implies the existence and the uniqueness of these advanced and retarded fundamental solutions that are called G plus minus, and they map from C naught infinity of M sections in E to C infinity M values in E. And then the difference between these two, so G equals G plus minus G minus, is a solution, is an operator that can be used to solve the Cauchy problem. Okay, so I just said that one can construct these things by doing, a lot of steps, but in fact there are a lot of steps. So it's a little bit like pulling yourself out of the swamp with on your own hair. So if you don't follow the steps in the right order, then this doesn't work, and you're drowning, and we don't want to drown. So I just wanted to make a couple of remarks because this is actually a really beautiful theory. And so the classical thing to do for hyperbolic evolution equations are energy estimates, right? And there is a way actually to do this completely algebraically without energy estimates, and I just wanted to point out this to you. So first of all, one remark that one can make here is that G plus minus extends in a very canonical way to a much bigger space that I call C minus plus 0 M comma E. So these, and it acts as an operator on this space. So this is just the inverse of P acting on the same space. So now what is that? That's the space of future and past compact supported functions. So here I wanted the support of F intersected with the future or the past of any compact set is compact. For any compact subset of M. So what does this look like? So a typical past compact set, for example, is something like this. Yeah, so if you take a point here, or compact set K, and you take its past, then you get something compact. So why does this immediately extend to a continuous operator on much bigger space? But it's very easy to understand, because if you want to understand what happens at this point, so you want to understand what this here at this point, all that matters is what's in the, for G plus, is what's in the past of this point, right? So what you can then do is you take a cutoff function and localize in the past of that point, and you won't change the result until you apply it just to that. So it's very simple to understand that. Okay, and now you map from the space to itself. And P is just the inverse of that. And for uniqueness, that's ideal, because if you're in an algebra, so yesterday we were talking about vector spaces over fields. So in groups, it's also true that the inverse is unique. You remember that? And so if you have a left inverse, for example, then this duality argument, because the advanced retarded fundamental solution is actually the same as the one of the adjoint of the adjoint. So you can, if you have a left inverse, that implies the existence of a right inverse, for example, because taking the adjoints will flip the order of multiplication. So a left inverse, for example, on this space will automatically guarantee a right inverse, and then the inverse is unique, so any left inverse will also be a right inverse. So you can see that there is a lot of beautiful algebra going on here that is behind this construction. So you get uniqueness of the local fundamental solution in this way. So I said you can construct these things locally. So the construction goes like this. You construct them locally using the Hadamard series and some kind of von Neumann inversion. And what you then get, and here is another remark, next remark, is that it's enough to construct these things locally, and then you can patch them afterwards together. And the way this is done is you pick your Cauchy surface, for example. So you take a little subset of this Cauchy surface, you call it, so that's an open subset, sigma dash. And then you can consider something that luckily Dietrich has already explained. That's the domain of dependence of this other Cauchy surface. So the domain of dependence of sigma dash. So that's, and I don't want to call it the domain of dependence because I like to call it the diamond, because it sounds, it's much shorter, and it also, I don't know, it has some appealing sound. Okay, so we have the diamond here over sigma dash. And so what's that? That's the set of points that intersect sigma dash. If you start there and you take any causal curve, starting from there and going to the past, you intersect sigma dash, right? So take the set of those points and take the set of points where this is true for the future, you get something which is also globally hyperbolic. So this is globally hyperbolic itself. Why? Well, because it has a Cauchy surface, namely sigma dash. And now, because of this old theorem by Geroch, or the more advanced smooth version by Bernal Sanchez, you can foliate it into Cauchy surfaces, and of course that looks like this, right? These are all Cauchy surfaces, and eventually you get the whole space by foliating it into Cauchy surfaces. So now what you can do, therefore, is construct G on this small thing here. And the other remark that I want, so you get the solution of the Cauchy problem for that. And then there is another beautiful argument using linear algebra that shows that if you have you can solve the Cauchy problem, it's actually the solution is unique automatically. And the reason for this is, so existence of Cauchy problem implies the existence, no, it implies the uniqueness of the same. Why is that? Well, that's also very easy to see. So, for example, so if you make it easier to not talk about dual spaces too much, let's take the Klein-Gordon operator. So I've not managed to work it out for a general operator, but let's just take the wave equation. The m squared doesn't matter, so you can also do it for m squared. M could be 0. Then on the space of solution, there is a standard symplectic form. So if you have two solutions, u and v, so u and v are both in the kernel of this operator, smooth functions in the kernel of this operator. So what you can do is you can do normal derivative v minus v normal derivative u. And then integrate that over sigma. So and it's a easy exercise in integration by parts that this quantity does not actually depend on the choice of sigma. So it's a symplectic structure on the space of solutions. And the fact that you can solve the Cauchy problem, you get plenty of functions here, shows you that it's a non-degenerate symplectic form. So it's a symplectic form. It's not only a bilinear form, it's symplectic. And therefore, if you have two solutions that have 0 Cauchy data, you can produce a lot of functions u and v here to conclude that the Cauchy data must, if the Cauchy data must be 0, then the solution must be 0 for all Cauchy surfaces, right? That's the point. So you foliate it by Cauchy surfaces, you do this argument, you run this argument for every Cauchy surface, you get the uniqueness of the Cauchy problem. So that's not, I don't think that's a very hard argument. Energy estimates, you make a sign mistake and everything is doesn't work anymore. But this is very robust in the sense of being, if you make mistakes, it's still going to work. Okay, and by the way, so immediately implies finite propagation speed. Propagation. Why? Well, because if your initial data is supported here and 0 here, then the uniqueness of the Cauchy problem tells you, well, it must also vanish here. So therefore, the solution must be, in the complement of that. And you can run that argument locally near that future thing here to immediately conclude that you have finiteness of speed of propagation. And then once you have those two things and the uniqueness of the retarded and advanced propagators, you can use that to patch it all together and get a global solution. So that's the order in which one has to do things. And I think this one last step to patch it all together, that's where you need global hyperbolicity, is in an old paper by Choquet-Bruhat is carried out. So you can read that. So that's, it's a very old argument, in fact. Okay, so let's go back to doing analysis. So one major example that I also maybe forgot to last time to mention is the example of Minkowski space, n-1, and the wave equation, in which case you have this G plus minus is actually just equal to the Riesz distribution plus minus, oh, I think it's upper index here, 1 of order 1 minus n over 2. So you can see, for example, if n is 2, this is just constant homogeneity, and so this the reason why the wave equation has that type of homogeneity. So this would be a distribution that is homogeneous of degree 2 minus n. Well, if you Fourier transform it, it has degree minus 2, right? And then the Fourier transform introduces this extra homogeneity, and well, clearly the Fourier transform has that degree of homogeneity because it solves, psi squared times the distribution equal to 1. So, primary school mathematics will give you that 1 minus n over 2. Of course, you still have to check that this is a fundamental solution, but it is. And in this case, so G plus minus G minus, which is G, so let's call that R, so that R is the difference between 1 minus n over 2, so R is equal to, R beta is equal to R plus beta minus R minus beta, so we all take these differences here. Then you can write down this fundamental solution explicitly in Minkowski spacetime. There's something missing that I also wanted to say. Maybe it's in another page. Okay. There it is. Yeah. So it turns out that in Minkowski space, because of translation invariance, G of x comma y, so the distributional kernel is just basically a function of x minus y, and you wonder what this G is. But G can be written actually as a sum of two, or as a difference of two distributions that I call G plus and G minus. These are not the R plus and R minus. They correspond to the sign in Fourier space. And in fact, there is a formula that you can find in Herman's book, but I mean, physicists know this formula very well. So I think it's 2 pi n minus 1 integral over R n minus 1 e to the I x comma xi plus and minus e modulus xi 1 over 2I xi modulus e xi. So as you can see, yeah, there is an X missing. Oh yeah, I was too fast, clearly. Yeah, you're right. I can remove the X here again. So the G, what this says is, well, maybe I should introduce more space. Is it still not right?
G plus minus on the other side of the integral.
Where? What did I do? Oh. Okay, let's start again. So shall I? Okay, so I say G of right. Let's do this very slowly, so that I don't make a mistake, right? And then yeah, okay. So G plus minus of x equals this of t comma x, right? So it's a new x here. So x here is spatial, so let's underline it. Now it should be okay. The whole point of this is just, okay, so there are two approaches to this defining these homogeneous distributions, the Riesz distributions. One is to write them down in coordinate space, what is it called, configuration space, with x, and then do analytic continuation. Another one is just writing down the Fourier transform, essentially, of this distribution. And everything that the Hadamard expansion does has a translation in terms of writing things down in terms of oscillatory integrals. And that's what I want to discuss today. But these are kind of equivalent, these approaches. Okay, last remark is somebody asked me last time, how do I know that in the Dirac case, the fundamental solution commutes with the Dirac operator? And I think that's a really good question. But in fact, it's just a general fact, a general remark. That was special remarks, and now we are making a general remark. If you have an operator L, let's say it's a differential operator, which maps, we'll do this. Okay, let's say it's a differential operator, just for simplicity, on M, taking acting on sections of E. So if we have an operator like this, and L commutes with P, then L also commutes with G plus minus automatically. Why is that? Well, a differential operator leaves that space invariant. And now we use that group theory argument again. So if you commute with something, then you also commute with the inverse. That's the argument. So more generally, any operator that actually leaves these two spaces invariant. So these two spaces here, invariant. So also translations, space-like translations, time-like translations, Lorentz transformations, as long as they don't change the time orientation, will have to commute with G plus minus as well, as soon as they commute with the operator P. Okay, so that's just a general argument. And we'll come back to that later when we have a killing field, because that's also true if you have a killing field, right? The killing field will have to commute with this. There is some kind of natural, G plus minus inherits all the symmetries of G plus minus because of this uniqueness that we have. Good, so let's go into Fourier integral operators, FIOs. And I'm very nervous to give this in front of Maciek, but I think I'll be so vague that I cannot be pinned down. So FIOs. And I'm going to use the homogeneous one, so no H. H will be 1 from now on. But there are some things that make the life easier. And one is this, so some notations. So the first thing is something that is very common in microlocal analysis, to put a dot on everything, meaning that you just take away the 0. So for example, not the dual, but so for example, the cotangent bundle with a dot, I'll just remove the 0 section. Or in a similar way, if you have Rn dot, that's just going to be Rn without 0. So that's the first notation. And then the second one is the notion of a wavefront set of a distribution in, let's say, it's in an open subset of Rn. So that's just, I'm going a slightly different definition, but I'll say that this is equivalent in a second. I find a piece of chalk somewhere. So we say that, so x comma xi, so in is not, we say by definition that this is not in the wavefront set, given an element x comma xi in R and U cross Rn dot, right? So which is the same as the cotangent bundle of U in fancy language, cotangent bundle of U with a dot on it. We say that this is not in the wavefront set of U. By definition, if, okay, now I have to make a root bracket, so if for some cutoff function phi that is compactly supported and smooth in U, that does not vanish at x, not equal to 0. You can actually make it equal to 1 in the neighborhood of x if you want to. We have the following estimate. So we localize our distribution at the point x. We take its Fourier transform that has a variable eta. And then I want that near this xi here, in the conic neighborhood of xi, this is exponential, is polynomially fast decaying. So I think the Japanese brackets were already introduced. I'll use those. So I have this decay for all eta in a conic neighborhood of xi. So this is an open conic neighborhood of xi. But thanks to Maciek, there is another characterization of that. That's also the same as saying that, or at least so in case this is a Schwarz distribution, so U is a Schwarz distribution, and you can always make it a Schwarz distribution by localizing it. This is also the same, so now I actually didn't prepare that, but I was just going to claim it. Yeah, what is it? So I take the FBI transform, but the one with the twiddle on it, so that got this phi removed. And then I take U, and what do I have to take? Y minus I eta. And I want this to be smaller than Cn. Well, I can say that this is of order h infinity. Sorry, I take that back, that h is equal to 1. So now h is going to be allowed to go to 0. And so this is for all y comma eta near in an open neighborhood of the point x comma xi. So that's basically just a reformulation of that, but with the extra property that you use the Gaussian to zoom in and then Fourier transform, but it doesn't actually change this wavefront set. So that's another characterization. So that makes a nice connection to Maciek's lectures. And of course, you get the analytic wavefront set if you want this to be exponentially decaying. Okay, so facts are that the wavefront set is actually a subset of the cotangent bundle of M if U is a distribution on M, by which I mean something much longer, by which I mean if you make a coordinate transformation, then the wavefront set will transform like as a subset of the cotangent bundle. So that's the statement here. And the other one, if you take the projection of the wavefront set of U, this is going to be the same as the singular support of U. And the analytic version was explained 2 days ago, I think. So that's very similar. The difference is to the analytic category, and so this definition is not so easy in the analytic category because you don't have that cutoff function here, right? There is no analytic cutoff function. So yes, the smooth case is a bit easier here. But so then there is this wavefront set calculus, which in my opinion is due to Hermander, and it very beautifully summarizes, what you can do with distributions. Of course, you can't do certain things with distributions. You can't multiply them, or things go horribly wrong if you try to do it, or you can't restrict them to hypersurfaces and all kinds of things. But the wavefront set calculus allows you to do it under certain conditions on the wavefront set. And I think I need only one of them, but if I need more, then I'll introduce them later. But there is one that is really interesting when you want to analyze integral kernels, and just state it, and maybe give you some idea of how to prove it. It gets going to be more and more difficult, technical now. So Hermander's wavefront set calculus. I'm actually not sure who invented it, but I think it's due to Hermander. I think he introduced the wavefront set in his article on Fourier integral operators, volume 1. So let's suppose we have an integral kernel. So this distribution in M cross M, and because it's going to be so technical, I'm going to skip the bundles. Okay, so you can always put the bundles back if you want. There's no change. We have two manifolds, M1 and M2. I have an integral kernel. And what do I want to say? But if this is properly supported, then this defines a map. K defines a map from C0 infinity of M2. And so you take this is just the Schwarz kernel theorem. So you take the variable y and you multiply it by a test function in the variable y and you integrate over y and you get something that has a variable x left over. And so usually this is going to end up in d dash of M1. But if it's properly supported, well, that's basically just the same thing as I'm saying that the following is true, that's actually going to be a compactly supported distribution now. So this defines a map from, is that right? Yeah. Oh yeah, because I haven't, so if this is properly supported. But now let's assume an extra condition. So assume that the wavefront set is actually much better than what it could be. So by the way, so given any closed subset of the tangent bundle, there is a distribution that has that as a wavefront set. So it can be anything. But assume that it's not anything, it's something else. It's that you don't have points of this form in the wavefront set. So x, 0, y, eta. And I intersect that with the wavefront set of k. And suppose that this is the same as, so I'm actually not sure if I need that, but you know, you can never be safe enough. So y, xi and y, 0, so these are also not in the wavefront set. So this is empty. Yeah? So there are no sets that are just in this direction where there is a 0 here in the wavefront set. That's not allowed. Then this actually defines a map from distributions to distributions. So then we have continuous maps. So K defines a map from C0 infinity of M2 to C0 infinity of M1. And it extends to a map from E dash, or from D dash by duality, I guess. Maybe that's why I need this other one. M2 to D dash of M1. And also compactly supported distributions to compactly supported distributions. Okay, so that's already quite useful because it also tells you how things transform. So and you can actually compute the wavefront set of k times u. So if u is a distribution, this would be a subset of the set of x, xi. Well, is going to be in the cotangent space of M1 dot with the property that x, xi, y, minus eta is in the wavefront set of k, and y, eta is in the wavefront set of u. So I think I have this correct. So this all looks very complicated, but it's actually not. Because what it tells you is, so somehow the points in the wavefront set, you know, you have points here, eta, and points xi, right? So if, write it down. So if x, xi, y, minus eta is in the wavefront set of k, what this means is it can map elements in the wavefront set y, to elements in, it maps the wavefront set of a distribution from y, eta to x, xi. That's what it does. That's what this means. So it's actually something about the mapping property of something. So for example, pseudo-differential operators, they only have their wavefront set when x, xi, when xi is equal to eta and when x is equal to y. In this case, it means they leave the wavefront set unchanged. So microlocality of pseudo-differential operators is encoded in the wavefront set of their integral kernels. And this, you know, general kernels, they just have bigger wavefront set, and you can do more things with them. For example, transport the wavefront set from one to another place. Okay, so what's a Fourier integral operator? A Fourier integral operator is just a special case of something like that can, in the same way as not every distribution with that wavefront set that I explained before is a pseudo-differential operator. So Fourier integral operators are more general objects that have some kind of asymptotic expansions in a symbolic way near those points where you're in the wavefront set. And I hope I can explain this now. So I don't want to go into much detail. I just want to give you that because I'm going to use the Hadamard expansion actually. But this has its advantages as well, as you all know. I mean, who doesn't like oscillatory integrals? Okay, so what's the Fourier integral operators? These are so FIOs are such operators. So there is a bit of a but the notation is actually not uniform. Some people say, does an FIO have to satisfy this or not, right? But I would say yes. You know, if it's a reasonable map, I think it should be satisfied. So, okay, there are operators that satisfy that, and there are some kind of conormal distributions in the following sense. So these are such operators with kernels given by oscillatory integrals, given by integrals of the form so I of x. So now I'm going to use this notation here. So I of x is going to be a distribution, right? It's not. Don't try to evaluate that at x, of course. So it's an informal notation. So here are these magic factors that can give you a lot of headache if you try to do computations. So over 4, then you have r to the power n. So this is some kind of extra space where you have some variables, e to the I phi x comma theta, no h, but if you want it semi-classically, you know, you can put an h here. And then there is x comma theta, d theta. Okay, now I have to explain all these things here. So the first thing, this is a distribution. So if you want to make sense out of this integral, you should first integrate with respect to x and the test function, and then do that integral. So what's phi? So where phi, and I think now we link very nicely with Maciek's talk yesterday. So phi is actually very similar to that. So it's a non-degenerate phase function. Which means that it's a, let me see, phi is a smooth function on, so U is the, you know, the open set, which is going to be the product in applications, but I'm just going to define this type of distributions. And then we have Rn dot, so it's not going to be smooth up to 0. Yes. So satisfies the following properties. So 1, phi x comma lambda theta equals lambda phi x comma theta. So it's homogeneous of degree 1 in the theta variable. So that's when lambda is greater 0. So positively homogeneous of degree 1. Then non-degenerate d phi equals, well, not equal to 0. So d phi means in both variables. And then we have this next condition here, which I look at the critical points in the theta direction. So these are the point x naught comma psi naught, theta naught, subset of u cross Rn dot. Is the property that d theta phi of x naught comma theta naught is equal to 0. Stationary points with respect to theta. And I'm assuming that this is an n-dimensional submanifold. So with d phi an n-dimensional submanifold with tangent space so that's where the linear algebra comes in. So the tangent space should be dc phi equals the kernel of d partial derivative phi. And then you can do that thing that Maciek did yesterday. and use that as a canonical transformation to get a Lagrangian submanifold of the cotangent space of U. There is this map. Where? Yeah? Kernel. So you take the theta derivatives. The kernel, the D. Yeah, so that's the derivative. No, in both variables. It's a non-degeneracy condition, right? I mean, think it through. I haven't. So what we really need, and that's basically the condition that I want to use. So then we have this map here, x comma theta, which is mapped to x comma the x derivative of phi. So this is where symplectic things come in. So this is a map from C phi to the tangent space of U. So this becomes a Lagrangian submanifold. So it is a Lagrangian submanifold. And it's immersed. So you can think of this here as a subset of T star U. And I want to give this a name. So this is, the image of this is, was it called lambda phi yesterday? It's certainly a reasonable, yeah, let's call it lambda phi. Yeah. Okay, so that clarifies what the phi does. And what's the A? So A is, everybody who loves, has Hermander as a nighttime literature. So A is just going to be a symbol. But I'm going to use the polyhomogeneous symbol class, so which means AX is a symbol of order M. Here there is the dimension counting, n minus 2n divided by 4 on U cross Rn. So, so I want this to be polyhomogeneous, which makes it a bit easier to define, and it's also enough actually for most of the applications. So this means that for large theta, there is an asymptotic expansion that can be differentiated, and it looks like as follows. So there is full asymptotic expansion, k equals 0 to infinity. Some test cutoff function in the theta variable. AM, oh, okay, so m plus, oh, that thing here, m plus n minus 2n divided by 4. And then I have to improve every time I make k larger, it jumps by 1. And these are homogeneous terms. So that's all a subscript here in case that's not clear. Let's move the A up here a little bit. So these are homogeneous of whatever is written there. So A alpha is, so in this formula here, A alpha is positively homogeneous of degree alpha. So, okay, a positively homogeneous function, of course, cannot be smooth, and that's at 0. So that's why you add this cutoff here. But in this business, what happens at infinity is the important thing. And so you just say, well, this for large theta, you can expand it into terms which are homogeneous in theta. Like a power series in theta or something like that. Good. So this cutoff function, chi x comma theta, is equal to 1 if modulus of theta is greater or equal than 1. So just, this only modifies the functions near theta equals 0. So modifications of this type give rise to smoothing operators, so we don't care about smoothing operators in this business. So smooth kernels, we only care about singularities, and the singularities are then encoded in this thing here. So the technical part is now over. We can relax a little bit. So for me, this is technical here. But I think this is actually, maybe elementary in some sense, that it's quite old. It's certainly covered and been generalized to much bigger symbol classes and allow much more general functions depending on age, for example. So the point, what's the whole point of this? So the main point of this is this type of formula allows you to do stationary phase expansions. So everything boils down to, if you want to understand how this behaves for large values of theta, if you convolve it with another function, or you multiply it by another function, you integrate, the type of integral that you get is going to be a stationary phase integral that you can analyze using the method of stationary phase. And that is the reason why we want to restrict to these types of integrals here. And there is a lot of geometry behind what happens if you change the phase function. Can you write the same operator with a different phase function? And maybe, and it turns out that it all depends only on this immersed Lagrangian submanifold. That's what actually I think Hermann worked out, that the data that you have, if you change the phase function, there is some kind of symbol calculus that goes with it, and there is this principal symbol here. Oh, that's too far away. Oh, that's a multifunctional tool here. So of course you want to call the top term here the principal symbol, right? But usually the principal symbol is something that transforms nicely on the change of coordinates. So here you can think of it as a function on the space of critical points, and then it becomes a function on this immersed Lagrangian. It's like, I think exactly what we had yesterday. But how does it change if you change the phase function? And it transforms in a non-trivial way. So it's not really a function on this thing. There's a more geometric interpretation. It turns out that it's actually half density. And I think I was going to put that a little bit on the rug. But so there is also, if you look at the stationary phase formula, there is the signature of some quadratic form in it, and then there is a determinant. So the determinant is going to be the half density part. Then there is this phase function which gives rise to the so-called Maslov bundle. But you don't need all these things. The only thing I say, well, in local coordinates, it can be written like that. That will be enough. Did I miss something? Anyway, so we're dealing with these types of integrals. So the half density, so there is this half density, which is AM, so the top part, plus n minus 2n divided by 4, so that one. This is going to be a homogeneous function of x comma theta, but you can think of it as a function on lambda phi. And then there is a canonical half density here, which I call dc phi, which comes from this phase function, essentially by forming this determinant. And I think I wanted to prepare it and postponed it, and then I forgot. So I'm not going to specify it now because that doesn't work. Maybe some can tell me. So there is, anyway, so that's a canonical half density that comes with this. And so there is an invariant quantity. It's called the principal symbol. It's called principal symbol. Well, phase functions don't have to have the same signature. So there is this extra, there's an extra factor here. So the principal symbol is also not a function. It's a section, the so-called Keller-Maslov bundle, but that's just something you change from one phase function to another. There is a way to keep track of it. That's all that says. Okay, so here is the theorem. So all this work is not for nothing. So one thing that you get out of the stationary phase formula is that the wavefront set of I, of this oscillatory integral, is a subset of L phi. So why is that? Okay, I'm going to wave my hands. First of all, I don't have that much time, but also because I think that would take me much longer, especially to make it completely rigorous. So what you want to understand somehow the Fourier transform of that, right? So you want to understand in which direction does the Fourier transform of this decay. And so you get a phase, you get this extra term from the Fourier transform, and analyzing in which direction that decays will of course end up with understanding how this phase, where this phase becomes stationary. And that's going to be exactly that condition here that you are on lambda phi. That's just the computation. That's how it works out. Okay, making it rigorous is a bit harder then, because you're not precisely in the case where you can immediately apply the stationary phase formula, but you can do it. So it's at least to understand where this comes from. Yeah, so that's the first thing. So this is called the canonical relation. So so what's an FIO? So U is just going to be U1 cross U2. So instead of on one variable, you have two variables. And then this lambda phi will be a subset of the cotangent bundle of U1 times the cotangent bundle of U2. And you will have that wavefront some condition satisfied. And so this wavefront set here will give you something which is called the canonical relation inside of the tangent bundle times cotangent bundle here. So it's very good, I think, to do an example. Okay, I'll just write down here. So K is in IM of U1 cross U2 lambda phi. And then M is called the order, and this top term is called the principal symbol. Okay, it needs an example, I think, and we already had one because I wrote down this G, and so that's actually the contents in this famous article FIO by Doistermaat and Hermander. Volume 2. But it's written in such a generality that it takes actually quite a bit of time to boil it back down to the wave equation. So I'm going to tell you what the result is for the wave equation. So it says the following: if you take this operator G that I think we all now agree solves the Cauchy problem, so this is going to be G plus minus G minus. This is actually of this form. So it's in I, it's an operator of order minus 3/2 on M cross M. Okay, so in the same way as you can construct pseudo-differential operators on manifold, you can also talk about Fourier integral operators on manifolds. You just use partitions of unities and glue them together, and you work modulo smoothing operators. I'm not going to describe how to do that. And then there is this canonical relation C, and I'm telling you what this is. So C consists of the points x, xi, y, minus eta, with the following property. So xi and eta are null. They are null covectors. Oh, I actually had a notation for this. So n, right? They are not equal to 0. So in particular, this condition there is satisfied. So they are Fourier integral operators, and the canonical relation is given by the geodesic flow. So the x and xi must be related by the time s geodesic flow, where s is some real number, y, eta, for some s greater 0. And no, for some s actually, some s in R. So that's a global theorem now. So the Hadamard expansion was only local, right? That's a global theorem. It tells you actually how, it's called the propagation of singularity theorem. It's actually a refined, well, there are various versions of the propagation of singularity theorem, but this implies the propagation of singularity theorem because it tells you how solutions of the wave equations propagate. What's the principal symbol, you ask? So with principal symbol being computed in this paper, very confusing, of course, everything, because minus I times 1/2 times square root of 2 pi. And then there is this dc here, which I'm going to specify in a second. So that's the principal symbol. You can find this statement up to the factor 1/2, and I will comment on this in a second in this paper, because all this is very confusing. Yeah, I'm going to comment about that too. So if you only consider phase functions which are, continuously changing, then you don't need the Maslov part. So you just need to specify one, so to say. Okay, so I need to really concentrate now, not to get this wrong. So we have to we can parameterize this here, and we can parameterize it by starting at x, psi, x, psi. Right? And then what we can do, once we do that, we can flow out with two variables. We can flow with the geodesic flow in this variable, and we can flow with the geodesic flow in that variable. So that gives us a parameterization of this canonical relation by points of the form x, psi, x, psi on a Cauchy surface. Okay, so we'll fix a Cauchy surface now, just for a moment, and in fact, we'll come back to this tomorrow. So what's a null vector? So there is a unique way you can write the null vector as the lift of a tangent vector, of a cotangent vector in the Cauchy surface. Okay, so the null vectors are isomorphic to the cotangent space of the Cauchy surface. So n is actually isomorphic to T star sigma. That's why I use global hyperbolicity. So every null geodesic somehow. Yeah, so no, we need to parameterize, right? So we can flow in. Yeah, okay, yes, that's right. So there is a forward and a backward one. So you're right. So there are two copies. It depends if I want them to be oriented or not. Yeah, that's right. That's right. So yeah, maybe I should multiply it by 2. Or times 2 points, 1 and 2. Yeah, that's right. So there are two orientations. And so n cross n here is parameterized by this parameter r here. But the cotangent space, so it turns out that this is a non-trivial theorem, but turns out that the symplectic structure on the space n does not actually depend on the Cauchy surface. There is a symplectic form here, and therefore a half density that is canonically given on T star sigma. That gives you a half density on this, and you take this half density and you take this ds, this parameter here, you tensor it with the other one, from the other n, and then you take basically the square root of the volume form on T star sigma that you get from the symplectic structure, which is completely invariantly defined. So dvn, so to say. I'm not explaining all this, but that's this. There is a density, and you take the square root of this density, and it gives you a half density. And so this half density is given in Thematic except for this factor 1/2. And it's because I use the geodesic flow, and they use the Hamiltonian flow of the principal symbol, and they take an operator for the 1. So that's where the 1/2 comes from. It took me a while to hunt down the 1/2, but that's the canonical relation. And so you see, this is simple enough. And this corresponds, in the Hadamard expansion, this corresponds to the first term. But this is a bit better because it works for all times, and we're actually going to need that. Ooh, okay, I have 5 minutes. And now we're going to boil this down. So you see, I got a shirt. It says spectrum analysis. My wife got it for me. It was like reduced from 10 euros to 5 euros, presumably because of this spelling error. I should say spectral analysis. Nobody wanted to have it. So what does any of this have to do with spectral analysis, right? Spectrum analysis. So, and in order to prepare us a little bit for what's coming the next days, I thought we'd do the simplest example where this boils down to spectral theory on Riemannian manifolds. So what does any of this have to do with spectral theory on Riemannian manifolds? But turns out that this understanding of these things actually led to the so-called Thematic wave trace formula. So it's already something that is I think, quite non-trivial. So understanding this even gives you already something in the Riemannian case. By the way, this construction of this thing as a Fourier integral operator is very similar to the Hadamard expansion. You start with the top order term, which is fixed, and then you improve order by order. So same idea, yeah. I think the next one is, yeah, but I don't know. I mean, there are, in the sense of the Hadamard expansion, I mean, has these lower order terms. And I think I'll give you a lower order term on Friday, and then you can decide whether or not it's invariantly defined. Okay, the ultrastatic case. Well, I have only 3 minutes to do that, but I think I'll manage. Okay, we restrict ourselves now to something like this, where the metric is of product type. So H is a Riemannian metric, and then the Laplace operator is just d2 by dt squared minus Laplace. My Laplace operator seems to be negative. I hope I'm not going. So what's the retarded and advanced fundamental solution? Let's maybe write down only the plus one, because the minus one is pretty easy too. So that's theta, that's the Heaviside step function, t minus t dash. You can see that switches it on, right? And then you have sine Laplace minus Laplace to the power 1/2 t minus t dash divided by minus Laplace to the 1/2. So that's easy to verify. So what do I mean by this? That's an operator. So I take the kernel of these operators in the x variables, so it's x and x dash, and then in the t and t dash variables. So I get a kernel in t, t dash, x and x dash. Okay, so that's how this is understood. And that turns out to be the retarded fundamental solution. The advanced one, okay, so minus, plus, minus, minus, plus, maybe like that, also plus, minus. So what you get if you take g plus minus g minus, everything cancels out magically, and you just get sine minus Laplace to the power 1/2 t minus t dash divided by minus Laplace to the power 1/2. By the way, there is no problem here dividing by this operator, because the function sine x divided by x is holomorphic, right, at 0. So that's, everything is well defined. Okay, so this is going to be this here. And so what do we want to compute? We want to compute, so now I think we are in the wave trace formalism. So what we want to compute this here, cos Laplace to the power 1/2 t. And you want to compute that as the trace of that. What do I mean by this? Well, this is a distribution on R. So this means when I smear it out with a test function, yeah. So maybe I have to write this down again. Not very good planning. So I smear that out with a test function phi of t. What I get is the trace of phi hat. I hope that's right. If there's a factor missing, well, I think some convention of the Fourier transform will be fine. So for phi in C naught infinity of R even, so phi of x equals minus phi of minus x. So if it's even, right, it gets you the cosine. And so that's just the Fourier transform. So thanks for that. Yeah. Okay, you can see that this is trace class because that's Schwartz, right? And then you have the eigenvalues, and basically just sum over the eigenvalues with that test function plugged in. So you can see that this is well defined if you know that the eigenvalues don't grow very fast. And so note the following couple of things. So from calculus, of FIOs, there are several conclusions that you can make now. Namely, if you just look at the integral kernel of this here, so this is going to be, you take this distribution here as a distributional kernel and you smear it out in T, you can use this wavefront calculus to understand that the smeared out version has actually a smooth kernel. A smooth kernel on a compact manifold, so maybe I should add that in this case I want maybe this sigma to be compact. So the smooth kernel has a smooth kernel, and if it's a smooth kernel, it must be a trace class operator, or smoothing operators are not only trace class; they are in all Schatten ideals. And because of this, any function applied to this operator, any Schwarz function applied to this operator is trace class, automatically implies that the spectrum is discrete. The spectrum of Laplace to the power 1/2 is discrete. So you see, this is a Lorentzian argument, and we're going to use that in the Lorentzian case in the next couple of days. That's not how you normally prove the discreteness of the spectrum. But it's actually a nicer, well, you have to do all this calculus, but it's a nice way of doing that. But there are more things, and I'm not going to tell you. So you can analyze the singularities of this wave trace, and it turns out that you get the Weil law from it, and you get trace formulas from it. And because all these things are spectral invariants, you can do inverse spectral theory. And so there is a long story here in Riemannian geometry. And I think that's where I'm going to stop because I'm over time. Thank you very much. No. So it actually not, because it only holds near lambda phi. So that's a good point. So if you, maybe I'll get rid of this. So when your canonical relation is just x psi, and your phase function essentially is just x minus y times psi, right? So in this case, the Fourier integral operators are the same as pseudo-differential operators, and you localize near the diagonal, and it's enough to work near the diagonal because everything else is smooth, okay? Everything else is smoothing. If you work as a Fourier integral operator and you want to localize near manifolds, you have to work away from that. So that means that you have to, take your canonical relation and you have to localize near that canonical relation and then fetch things. So the diagonal is going to be replaced by your immersed Lagrangian submanifold. By C phi, sorry. Yeah. So yeah,
that was originally locally defined.
Yeah, but it was defined not on the same set, right? The set was, sorry, maybe I didn't make that point very clear. So FIOs, you have to replace U by U1 cross U2. So now there are two variables, and they don't have to be in the same set. Yeah. Can you point me, because I have no idea.
Just the I set.
That's the order. So M, because you see when you look at this.
The order of these eight.
Yes, so I hope it's still there. No, it's not. So yeah, because you remember when I said A is a symbol of order M plus blah, blah, blah. So that's the order of the symbol. So the top term, right, is as how bad can it grow at infinity. That's what stands here, that's right. And this plus n and so on, it makes sure that it's invariantly defined. So the order doesn't, because if you choose another set of thetas, the m actually changes because of some, descent formulas.
Remind me why there's this shift in the order.
So far, everything was fine.
I think it's when you compose them. Also, if you take the different. I mean, you have lots of choices for phase.
Yeah, but I think you want to see the computation, right? Is that right?
Yeah, that's where it comes from. Is it?
Yeah.
Like
No, well, I'm not sure if I want to commit to writing this down now, because it's not going to work. Yeah.
It's a convention, so that identity is an isomer.
Yeah. So
it's
yeah. So it's, I said U times cross Rn. So n was not the same as the dimension of U. Where? Oh, that. Yeah. That's right. So you can have many more variables. It's actually useful if you want to compose things or restrict things to have that. In fact, it's there is a more general class too. There is a little e also, the excess, which is very scary. But that's when, well, I don't know. I find it scary. Yeah.